Hey everyone, Olympia here. Welcome to our brand new channel, where we dive deep into science topics that go way beyond the usual pop explanations. Today, we're tackling something mind-bending. The Lamb shift. Why do atomic levels change? And trust me, by the end of this video, you'll see empty space in a whole new light. Alright, first things first. What's the Lamb shift? Back in 1947, a physicist named Willis Lamb, along with Robert Rutherford, noticed something really odd while studying the hydrogen atom. Quantum mechanics predicted that two energy levels in the atom, which we call the 2s and 2p states, should have exactly the same energy. But when they carefully measured it, oops, there was a tiny difference. This wasn't some rounding error or broken equipment. No, even after double and triple checking, it became clear that our beloved theory had a missing piece. So how small are we talking here? The energy shift that Willis Lamb observed was just a few 10,000ths of an electron volt. But don't let that fool you. This seemingly minor detail had enormous implications for physics. In fact, it was one of the first data points that would confirm something called quantum electrodynamics, or QED for short. QED is essentially our current best understanding of how light and matter interact, blending quantum mechanics with special relativity. And before you ask, yes, QED still holds up today. Physicists like Richard Feynman and Julian Schwinger used it to predict things down to 1 part in 10 billion. But back then, it wasn't even fully fleshed out yet. Okay, let's unpack this. Hydrogen's 2s and 2p states correspond to different electron configurations within the atom, and according to the old-school Schrödinger equation, they should be degenerate, meaning equal in energy. The Lamb shift shattered this assumption. What Lamb and Rutherford were actually seeing was the hidden hand of the quantum vacuum itself. Wait, quantum vacuum? Isn't vacuum just like nothingness? Not in QED. Here's the wild part. Even in so-called empty space, you've got a seething sea of virtual particles winking in and out of existence. These aren't the kind of particles you can detect directly, but their effects are very real. This constant buzzing of energy disrupts the electron slightly, altering its energy levels enough to create the Lamb shift. To visualize it, imagine you're on a perfectly still pond. Now, toss in a handful of invisible pebbles. The surface starts rippling, and those ripples change your reflection ever so slightly. That's kind of what the quantum vacuum does to electrons. And to be clear, this isn't some fringe idea. It's been tested dozens of times in laboratories, with even better precision since Lamb's day. Now, let's crank this up a notch. Physicists realized they could describe this interaction using something called radiative corrections. See, the electron isn't just chilling on its own, it's constantly emitting and reabsorbing virtual photons, tiny packets of energy. When you throw all these effects together, including corrections from the quantum vacuum, you finally get the adjusted energy levels. Think of it as the universe's tiniest debugging loop. Here's where it gets advanced. The Lamb shift also paved the way for deeper questions about quantum field theory. One debate, for instance, revolves around something called regularization. Basically, when calculating the vacuum's effect, you run into infinite results that make no sense, like dividing by 0. Physicists fix this using mathematical tricks to remove the infinities, but not everyone agrees this is the right way to handle it. Some think it hints at deeper, unresolved issues in our theories. And let me blow your mind further. This subtle atomic phenomenon connects to cosmic scales. Virtual particles and quantum fluctuations could play a role in the universe's expansion. That means the same principles causing the Lamb shift might also tie into the mysterious energy driving our cosmos apart. Crazy, right? So, why does this matter? Well, without quantum electrodynamics and the Lamb shift, modern technology would look very different. Things like lasers, MRI machines, or precision GPS. None of that would work the way it does without these discoveries. But there's still more to uncover. Are virtual particles really real? Or is that just a convenient model? And will a future theory, like quantum gravity, overturn everything we know about vacuum effects? For now, we can't say for sure. All right, I think we've gone deep enough to feel the intellectual vertigo, don't you think? Thanks for sticking through this journey into the lamb shift. Let me know in the comments which mind-bending topic we should tackle next. Remember, this channel is brand new, so your feedback helps shape its future. Like, subscribe, and share if you enjoyed this quantum rabbit hole. Stay cruised, stay hyper-focused, and keep questioning reality.